So we're still looking at the monsoon changes, which we attribute to ocean warming, land warming, and the contrasts. And I should have made it clear as to why the monsoon trend is actually negative. So here we said the monsoon trend is negative, and under global warming, we have been saying that actually the ocean warms and the land warms faster because the land has lower heat capacity. So if Indian Ocean has warmed and the Arabian Sea has warmed, then if land warms, warms faster, we should expect that the ocean to land temperature gradient. So this warming should have created a lower pressure, and this pressure would be high because it's less warming. So the pressure gradient would have increased and the temperature gradient would have increased. So we would expect the monsoon to actually increase. Why is that not happened? So I missed a key point there. Early on, I had shown a map of aerosols, for example, from pollution, from sulfate, coal burning, from dust because of droughts, and so on and so forth. So the amount of dust loading on the Indian subcontinent has been looked at, and there is something called solar dimming, or it is the reduction in the amount of solar radiation that reaches the land. That has also increased over time, and this has actually not allowed the land to warm as fast as it should if equal amount of radiation increase happened over land and the ocean. So that has actually caused the land to warm less than it should, and that has probably been the most dominant reason. I say probably because we don't know for sure if there were other reasons why the monsoon may have been decreased in addition to this solar dimming. So solar dimming, as far as we know, all the models show. In the models we can put the aerosols and take out the aerosols and then impose the greenhouse gases as we usually do for attribution. We see what the model attributes to attributes the difference in warming to, and the monsoon trends too, and all the models indicate that that aerosol increase and the solar dimming has been one of the main reasons why the monsoon has actually decreased. What does this mean for the future? Already there are claims by one or two papers that actually somehow the pollution and aerosol loading has decreased since about last 5 or 6 years, and that the monsoon has begun to recover. This has to be confirmed because we have to wait for typically 10 or 15 years before making sure that actually monsoon is headed back upwards. Otherwise, it might come back down again. Also, it is not clearly explained why suddenly pollution may have decreased. But satellite data show that there is some greening of some parts of India because of this increased rain, which indicates that maybe the afforestation plan or this idea of increasing forest cover to increase carbon sequestration by the Indian government may have also played a role in increasing the rain and reducing the pollution, and there may be a positive feedback. So we don't know these things yet, but right now it's safe to assume that the monsoon has been decreasing since about the beginning of the century, in fact. Okay. So keeping that in mind, we looked at further changes that are happening in terms of the delayed onset, earlier withdrawal, which is changed the length of the rainy season by a few days. So less rain, shorter rainy season, but if the extremes have increased so much, you can still rain less, because as we saw in 2018, for example, it has rained a lot over Kerala, but it is very deficient in northeast and over Gujarat and so on, and over much of central India. So you can do these combinations of rainy days, rain intensity, length of the rainy season with many combinations of total rainfall active break periods and intensities of active and break periods. What else has changed? This study also by Sabir Ali and his colleagues shows that with the warming, the so-called mesos or the northward propagating systems that we talked about have also changed, which makes sense because they are all related to each other. The onset is related to the northward propagation. So, if you look at this figure, is showing the lead lag relation, or what is often referred to as a Hofmüller diagram. So, it is HO, there is a more complicated spelling of the German name, but HOVMULLER, Hofmüller diagram. It shows that something starts over the ITCZ that's sitting in the equatorial region, so just south of the equator, and these systems propagate systematically northward into the Bay of Bengal. There is a lot of rain over the Bay of Bengal, but also there is interaction with the convection and the low pressure systems then that propagate into the Indian subcontinent from the Bay of Bengal. So, these mesos have a certain speed. So, the phase changes. So, remember, if it is active over the Indian Ocean, then it's a break period over the Indian subcontinent and vice versa. So, this system moves, and by then the Indian Ocean has changed sign, and that then moves north, then again the sign change. So, these speeds are related to the waves in the atmosphere. There are also waves in the ocean. We briefly mentioned for El Nino, for example. We haven't gone into the waves, but if you wish, you can look them up. Basically, there are just a few major types of waves that have certain dynamical features, which is the way direction of phase propagation, group velocity, how much energy they transport, and so on and so forth. So, that speed is compared here. For example, this is the speed under the non-warming conditions, and with the warming conditions, the speed has changed. So, actually the systems are now moving much slower than before, which would be consistent with the reduction in the total mean rainfall. So, essentially, if you are bringing in less of these rain bearing systems into the northern hemisphere from the southern ITCZ, you would expect that over a season that would amount to a reduced rainfall. It's not that simple because there are many other factors on how the total rain is determined. It's not just because of these northward propagating systems, but they are a major contributor to the total rainfall. So, just to keep in mind that not only the onset delay and the withdrawal advance, but also the northward propagating systems have changed in their speed. So, if you want to go from extreme events greater than 150 millimeter per day and so on, converting it into floods is still involves many factors. For example, if it has already rained, the soil may be already loaded with moisture. If more rain falls, then you produce more runoff. Or if you have a slope like the Western Ghats, like in Kerala, if somehow that vegetation has been changed, then the runoff increases. Or if you have cities where you have paved a lot of the area with cement and tar and parking lots and buildings and so on, they also don't have much surface to absorb all the heavy rain. So, then also the runoff increases. So, floods, extreme rain doesn't necessarily mean floods immediately, but there are many factors involved in converting the heavy rainfall into the slope itself will be important, and the amount of runoff generated. In other words, how much of the rain actually gets converted into water that is not going into the ground also matters. So, there are many reports already being discussed in the media. As you know, there was a report saying that none of the dams in Kerala have an emergency operating plan, for example. So, these are more difficult issues that goes from climate into decision making, hydrology, and how does an engineer decide to release the water based on the forecast. If the forecast is very accurate and he knows that by using many times, then he might believe it and release the water. But if the water is released, he has to worry about whether it is being released into a well or a groundwater recharge or the ocean, because if the forecast doesn't come through, if the forecast is not accurate, which obviously can happen sometimes because the models are never 100% right, then you want to be sure that that water is not completely lost to the ocean. So, there is some hydrologic planning is required, and such kind of work is also going on that connects climate information into hydrological information, hydrological forecasts and so on. So, this is showing the vegetation cover for Kerala Western Ghats over 1973, and you can see that by 1976 all these regions basically have lost the thick heavy forest cover. So, the green colors here are the forest covers, the yellowish reddish colors are plantations, and there is a lot of yellowish agricultural land buried in it. There are some water bodies buried in there. So, when the development or conversion to plantation etc. happens, oftentimes existing hydrological structures like water bodies are also lost. What do? The water bodies are basically natural reservoirs. When there is water being produced from rain, it tends to flow into these water bodies. That is why the water bodies exist in the first place. So, those also tend to get destroyed, and there are many urban developments as well in Kerala, as we know, and some open areas. So, the area changes in square kilometer for each is quite substantial, and the total area change is almost 38,000 square kilometers. For such a small state, that is not a small number. All these things will be looked at because obviously the government, state government and central government want to learn from the disasters that happen, like the 2018 flood. And the vegetation cover, the afforestation plan that government has in place must prioritize to address some of the regions which are more vulnerable to heavy rains, extreme events and flooding. So, such a hazard map is also now being produced, and obviously they will be more and more combined with the improved forecasts from the India Meteorological Department to make the big decisions. So, this is what I already mentioned. Lots of reports pointing out that just last year in 2017, Comptroller Auditor General had put out a report saying that none of the 61 dams have any emergency plans. That is not to blame someone, but that is to say they haven't been made aware of these changes in extremes and the changes in vegetation and so on. So, these things obviously have to happen. Just to put it back in the context of all over India, these are changes from satellite maps of land use change, again going from forest gain, forest loss, fallow and waste croplands, fallow croplands and various other land use types from cropland, shrubland, grassland, wasteland and so on. Very detailed map which shows the change from 1985 to 95 and 95 to 2005. And you can see some regions have seen fairly massive changes, and there may be some regions where we have already discussed the forest gain has happened, the green dots. You can look more carefully and find them. There are regions where more forest gain has happened. So, the human activity continues to happen in parallel. Some cities boom and they begin to take over the forest land and agricultural land as they expand, like Hyderabad or Bangalore or Delhi. And some regions the government is making more concerted effort to increase the forest land and so on. But having these kind of satellite data gives you a very nice overview of how to make hazard maps, because the vulnerabilities to natural hazards will basically combine amount of rain, extreme likelihood of extreme events, orography or the slopes, vegetation types, plus also there are human factors like is it rural area, is it urban area, There is also in accounting of data like how many women are educated and able to understand information provided from the census data. They can get all these kinds of information, and a district level and sometimes even taluka level hazard maps are created out of those, so that in the future better decisions can be made based on these informations from forecasts from climate and weather models. So, I will touch upon a couple of other points that I haven't systematically touched upon when we talked about the models. What are those points? So, these are basically called systematic biases in the models. So, the amazing thing about the models is you have an atmosphere, ocean, you have land, vegetation, everything, and you just give it the radiation at the top of the atmosphere. It takes that energy, distributes it, begins to generate winds, ocean circulation, temperature, humidity, rainfall, vegetation, clouds, snow, ice, everything, right? But despite how amazing they are at producing El Ninos, monsoon, La Ninas, and the longer time scale variabilities we talked about, like Pacific Decadal Oscillation, North Atlantic Oscillation, and so on, they have some biases. It's like having a car. New car may even have some defects, or you can think of it as comparing older cars to newer cars. Newer cars have better fuel efficiency and so on. So, the models are constantly improving based on the knowledge of what we know about the systematic biases that exist. I hesitate to use the word bias, but you can think of it as the difference between the observed value of something and the model simulation of that value. Such a value is shown here. One of the most important things we always look at is the sea surface temperature gradient in the Pacific. We remember we have upwelling and cold temperatures here, and we have the warm temperatures on this side, and this sea surface temperature is very critical because this heating, as I said, 5 meters of rain per year can affect global climate and weather, as it is very clear during El Ninos, for example. So, the observed temperature here says it is going, this is, I have to make sure that this is the Atlantic Ocean, not the Pacific Ocean. So, it is going from negative near the coast of, you cannot see it, of Africa to the coast of South America. So, it should be warmer in the west and colder in the east, but you can see that most models are actually going the other way and some models are way off, okay? Several degrees difference from observations. So, almost systematically all models are wrong in the Atlantic. There are many reasons. We do not know whether the errors in the Pacific affect the Atlantic or if Atlantic errors affect the Indian Ocean and so on, because these coupled system, vegetation error can affect precipitation, or precipitation errors can affect the vegetation. Those errors can affect the ITCZ, ITCZ can affect the temperatures in return, and so on and so forth. What is the critical error in the Pacific? We looked at the ITCZ and we said the ITCZ has a northward position compared to the equator, and there is this South Pacific convergence zone that we talked about, right. So, the South Pacific convergence zone, which is very critical for rainfall over Australia and so on. In the models, it is systematically made to appear much more sticking to one latitude instead of tilting this way from the northwest to the southeast. This makes a difference because that affects the winds, the circulation, the trade winds, and so on and so forth. So, that is typically referred to as the double ITCZ problem, where instead of having just one ITCZ here, models tend to have two ITCZs. This creates problems for its El Nino simulation and so on and so forth. So, this is a systematic bias that has existed for a long time, and I will show next what potentially can remove this error. So, the modelers are constantly trying to figure out whether this error comes from the atmospheric model, ocean model, or together, or comes from the land vegetation and so on and so forth. And in the Indian Ocean, the observations show that the thermocline depth. Remember what the thermocline is. There is a module on that you can look up, but if we think about temperature with depth, the temperature is warm near the surface and cold at the bottom, and there is a rapid transition which we called the temperature gradient or the thermocline. Cline is slope, thermo is temperature. So, the temperature gradient or the thermocline in the Indian Ocean is actually deeper in the east off of the coast of Sumatra and Java, whereas it is shallower off of the coast of Africa, east coast of Africa. This is critical because this means warmer temperatures here because this interface is deeper. So, the thermocline is like this in the east and shallower in the west. This makes a difference because how much cold water can be brought to the surface depends on where the thermocline is. So, if the model makes some error and brings up more cold water, because you can see that the model slope is almost completely wrong. It is almost flat or almost the same as the east. So, this affects the way this model will behave. And again, we do not know whether this is related to the flow of water from the Pacific into the Indian Ocean, or the errors in the winds themselves, or the errors in the monsoons, but there are also systematic errors in the monsoons in models. So, this potentially affects the monsoon and the monsoon potentially affects this error. So, in a coupled model, it is like a chicken and egg problem. It is like fight between two people. Once the fight is exploded, you often cannot go back and figure out who started what. So, that is kind of the system we are dealing with. So, that seems like bad news, but there is some additional details. For example, this is looking more specifically at the Indian Ocean, where we said the warm temperatures, for example, deeper thermocline here, so warmer temperatures, shallower thermocline here show colder temperatures. These is important because that determines the ITCZ, determines atmospheric convection. Remember the magic number of 28.5 or 28 degrees centigrade. This is just showing different models from around the world and different temperature ranges simulated by the model versus what is observed from data. And you can see, I will not go into the details, but the main message is that most of the models are systematically colder than observed sea surface temperatures. It could be because the winds are stronger, or it could be because the temperature gradients are wrong, and so on and so forth. I will not belabor the point, but in a coupled system, everything is related to everything. So, we just need to be aware that when the temperatures are warm, if you have a convective threshold something like 28.5, then if the temperature goes from 28.5 to 28, convection dies, which means the atmospheric heating changes, which makes large impact. And if it goes half a degree warmer to 28.5, it will start convecting, heating will change, circulation will change. So, when you are very warm, small temperature changes can make a big difference. That is like Bay of Bengal versus the Arabian Sea. We said the Bay of Bengal is so warm that if you try to warm it more, it will start to convect more, whereas the Arabian Sea still can warm without making a big change in the heating, because it is still well below the convective threshold. So, those kind of systematic biases and where they are in the warm region or the cold region can be very critical. That is something we have to worry about. So, what are some of the processes that are involved then? So, let us go back and think about the ITCZ. We said the monsoon sits here and the ITCZ is running like this. So, in the winter months, the ITCZ is following the sun and going this way. We said in the summer months it moves over here, but it keeps a piece here. So, we split the ITCZ, and we said that potentially allows the signal from the Atlantic to affect the Indian monsoon, as well as from this side Pacific to the monsoon as well. Right. So, ITCZ potentially is something very important, not only for us, for also West African monsoon, the Central American and North American monsoon, Asian monsoon, Australian monsoon, and so on. All the monsoons are linked by these ITCZ, and now in fact there are people are calling them as global monsoon. As we said before, they are not as dramatic as the Indian monsoon, but nonetheless every time you change the direction of winds because of ocean land heating differences, now we are calling them monsoons. So, the main question then is, we said before, why is the ITCZ remaining to the north in large part of the world ocean? We said it is because maybe land is more and that heating is more, but there are some details which actually seem to indicate that if you look at the temperature distribution, here what is done is you take sea surface temperatures at each latitude and then you subtract the mean temperature over that latitude. So, here the temperatures are colder than the mean temperature at that latitude, and here the temperatures are warmer than that mean temperature over that latitude. We know that is consistent because we know that there is deep water formation here because the Gulf Stream is bringing warm waters, and that is critical because that warms the atmosphere, increases evaporation, leaves the salt behind, which is what gives us deep water formation here. Whereas, over the Pacific, even though the winds are sometimes stronger, it is stormier, the temperatures are so cold and the water from the Arctic is making it so fresh that the evaporation is not causing deep waters in the Pacific. Why am I saying this? Basically because it turns out that the new data shows that new models results and so on show that when we consider the thermohaline circulation, which you remember is deep water formation here. So, all the blue water going south mixing with the deep water formation, bottom water formation in the southern ocean going into the Indian and Pacific oceans. So, the cold water is flowing out here, but flowing in here, getting converted to surface water because of mixing and so on, which takes hundreds to thousands of years, as we said. Eventually, that water is flowing back as the Indonesian through flow, as we said, and mixing with the Indian water that is coming back, and altogether it has to go back to compensate for the sinking water. That is what we called the thermohaline circulation. Why am I showing it again? Because if you look carefully, as I mentioned briefly before, this hemisphere is actually colder, this is much warmer, and yet we are moving heat from here to here. So, we are moving heat from a colder hemisphere into the warmer hemisphere. This is done because the ocean is forced by the atmosphere. The currents in the ocean are created by the atmosphere. So, the ocean is mechanically forced. What does that mean? The atmosphere is forced very differently. Atmosphere is heated by the radiation, some of it is absorbed, but mostly it is heated from below, and then it is evaporation, condensation and so on that is creating the winds and so on. So, it is mostly radiatively forced, whereas the ocean is forced mechanically by the winds that are generated radiatively. So, that is something to remember. So, as I said before briefly, if you move this heat to the northern hemisphere, which is already warm, to balance the energy, somehow you have to move that energy back to the southern hemisphere. Otherwise, northern hemisphere will keep on getting warmer, southern hemisphere will keep on getting colder, right. This is different than the equatorial pole temperature gradient we had talked about. That is still going on, but on top of this you have this meridional overturning circulation or the thermohaline circulation or the global conveyor belt. So, essentially that is what the ITCZ does. ITCZ is the atmospheric part of this heat transport. So, because the energy has to be moved south, the ITCZ or the energy equator moves to the north in the warmer hemisphere and collects the energy there through this Hadley cell. It actually moves energy southward. So, that also is the reason why we have now, for example, much colder temperatures in the southern ocean and the southern hemisphere than in the northern hemisphere. So, if you in fact look carefully at the equator to pole temperature gradient, which we looked at early on, it is asymmetric because from equator to southern pole the temperature gradient is significantly larger than the temperature gradient from the equator to the northern pole. So, constantly energy is being moved south, which means if something changes in the southern hemisphere, if there is somehow too much radiation coming into the southern hemisphere, that can affect how much energy ITCZ has to move to the south. So, in the models it has been argued that models are not doing the clouds correctly, hence the models are moving the wrong amount of energy to the south, and that is what giving us this double ITCZ in the model. Is that the case? Maybe, but this has to be understood in the sense, once you understand that maybe the errors in the southern hemisphere are causing the errors in transport here and creating the wrong ITCZ, then you have to go back and figure out how would you fix this problem, how would you improve the cloud cover in the southern hemisphere, and why are the clouds wrong in the southern hemisphere in the first place. Okay. So, the another hypothesis that got derived from the model relied on the mixing in the ocean that is called near inertial wave mixing. Inertial waves means what? You already probably can imagine Earth is a rotating system. So, everybody has an inertia. If suddenly Earth stops rotating, things will fly off into space, right. We are all standing steady because we are going with the system. If the system stops, we will go off. So, the same thing happens on the ocean. If wind blows suddenly and stops, the particle that is being pushed keeps moving because of inertia, unless friction stops it. So, that constant wind changes produce what are called inertial waves in the ocean, and when those waves break, there is some mixing of the waters, which means mixing of temperature and salt in the ocean. And why is that important? Remember that we said that the ocean has these thermocline and so on, which gives us a very steady situation. So, this is temperature and depth. If temperature is warm near the surface, cold in the bottom, we said that how do we know this water is eventually getting converted back to surface water in the Pacific and Indian Oceans? We are saying cold heavy water is going in, over hundreds and thousands of years it is getting converted back to surface water. If the system is so steady that cold water is sitting, heavy water is sitting at the bottom and warm water is at the top, how would this water get converted? Because that takes a lot of energy, and that energy, some of that energy comes from these constant wind forcing of the waves. What is the short message? This model, which had a double ITCZ, improved its near inertial wave mixing, and you can see that now suddenly this became very realistic, and it shows that they also improved things in the southern ocean. So, this hypothesis was saying that maybe something is wrong in the southern hemisphere, hence the ITCZ is wrong. This is saying that ocean mixing was wrong, which improved the transport by the ocean. That improves the southern hemisphere, and that improves the intertropical convergence zone or intertropical convergence zone or the ITCZ. Why am I going through this? Basically to point out that when you have a full earth system modeled, it is literally like you are a doctor who is trying to figure out what is wrong. If somebody has a fever, what is the cause of the fever? You have to kind of diagnose it properly and understand it. So, a lot of these things are focused on reducing the standard biases or differences from observations in the models. Is there any good news? Of course, there is a lot of good news. So, these are predictions from this year of the floods over Kerala and some parts of Maharashtra, I think, and this is from last year, the big Bombay flood. The Bombay flood happened on 29th August. This forecast is from 24th August. Full 5 days beforehand, the IMD forecast said there is a huge extreme event coming to Bombay. And as I said, they had already done a study on the 2005 flood and they had made some changes, and they have a comparative report showing that actually they handled the 2017 flood much better. Okay. So, this bullseyes here were quite accurate in terms of heavy rainfall events that happened on 16th, and this forecast is from one day before. I do not have an image for few days before, but even one day can save lives. If somebody is looking at it and saying we are going to have floods, you should take cover or move upstairs, whatever. There are many decisions that can be made. This is fantastic news, right? There is not only predictability of these extreme events, but actually we have now a system in place running in India which is issuing forecasts that are reliable. Of course, this has to be done again and again. So, the more people see that the forecasts are correct, the quicker they will react when they see a forecast. Okay? So, these are the take home points from this section on the Indian monsoon. So, we looked at monsoon variability and change. So, we could not understand monsoon change unless we understood most of the basics of the monsoon variability, which we did in terms of the equator, the meridional temperature gradient, the mesoscale systems called mesos, the monsoon intraseasonal oscillations, the temperature gradient that changes and onset happens, withdrawal happens, the active break cycles and so on. But overall, you have to remember that India and its neighbors like Pakistan, Bangladesh, Nepal, Sri Lanka are all highly vulnerable regions. Population densities are very high. So, if there is a flood or a drought, lots of people get affected by it. Non-local factors complicate the drivers of adaptation mitigation. What do I mean by that? We looked at the temperature relation with extreme rainfall and showed that over India, there is not much of a local relation. Local warming does not explain local extremes. Moisture is coming from the warming of the Arabian Sea. So, even if you improve conditions over land, if the Arabian Sea is able to pump moisture, what will it do to extremes as we go into the future? So, adaptation mitigation, which is focused on local factors like improving land use, forest cover, etc., energy use and so on. What will the warming around India do to Indian monsoon and our climate? That's a very difficult question, but with better models we will understand much better what to do with them, especially in terms of improving forecasts and reducing the impacts ahead of time. So, in that sense, improving predictions and projections is an absolute imperative for India, and just in time, in the last 10 years, India has invested several hundred crores into buying a new high performance supercomputing, hiring a lot of young scientists and building a good monsoon forecasting team, extended range and weather forecasting teams. Now, there are also efforts being extended into taking these forecasts of weather and climate and making decisions for farmers. IMD sends out several lakh texts to farmers every morning during the rainy season. There is fisheries forecast being done. So, there are extension of these forecasts into other sectors, which is very critical. So, the investments in weather and climate predictions in that sense are paying off. There is still a lot more to do in terms of applying these for health, the water quality and air quality, for example. Can you predict that pollution will be higher and let the older people sit at home, close the windows, use the fan, kids cover themselves when they go to school, etc. It's all possible. So, hopefully, that's where we will be headed. So, monsoon is definitely responding to global warming. There are many bad effects like increasing extremes and more intense active periods, more frequent break periods and so on, but we must continue these efforts to improve the models and start to include mitigation adaptation into these, which is what the projections are doing that will come out by 2021. So, you should keep your eye on that. Okay? So, this ends this section of the course, and We'll see you next time.